Okay, thank you very much. So the next speaker is going to be Brendan Hansknecht, which I've been told is the Americanized pronunciation. The real pronunciation is more complicated. I'm Italian. The English pronunciation is already way too hard, so I'll leave it at that. But he's a core contributor to Rock. So Brendan, please introduce yourself, if you don't mind.
Yeah, hi everybody. I'm Brendan Hansknecht. So fundamentally, I'm someone who loves diving into details a little too much, especially when it comes to performance and disparate aspects of that nature. So I work on compilers a lot, both like AI compilers and like Rock itself. And I love making language faster, making the compiler faster, just digging into these type of problems that require knowing the system details.
Awesome. I've actually watched quite a few of your live streams. Tell people where to find you and to please follow, share, like, subscribe, etc.
I mean, I don't actually stream that much. I may get back into it, but I'm always on the Rock Zulip if you just want to chat and discuss details. And then if I live stream, it's Hansknecht, except it's not spelled like my name. It's simpler because I just use the word connect, like the English word connect, to make it easy to spell.
Okay, so people, if they'd be interested enough, will be able to find you. So, well, please give it up for Brendan, and let's hear it.
Okay, so before we get started, two things that I want to just make sure of the slides. Do people like dark mode, or should I switch it to light mode? Dark mode sounds good enough. Okay, two, is this type of an animation going to be terrible?
Yeah.
We're good? Oh, I can turn it off. Okay, so we should be good there. And then one final question, general for everybody. How many of you would you say that the linker is like a significant chunk of time in your development loop? So when you go and you develop something, you're stuck waiting for it as part of the steps. Okay, that's roughly half. Okay. Yes. Now, on the other side of it, how many of the people who didn't raise your hands, is it because you use a dynamic language with, essentially no linker? About half of that. So a quarter of people just use dynamic languages. And then of the people that use a static language, about, I guess I would make 2/3 of them run into problems with the linker. And so this talk is linking can be fast if you cheat, Rock surgical linker. And I just want to preface this. This is cheating. Do not get angry at all the linker implementers because their linkers are too slow. Mold is an amazing product. Rui does a lot of great work. So please respect their work. But now let's look at how we can get faster than that. I guess quick little background if you want to talk to me later. I work at Modular. I mostly work on the AI compiler there, what's called the engine. But I pay attention to Mojo, and then I work on Rock. So if you want to chat about either of those things or system details, etc., come find me. So not too important. We're just going to give a little background, explain some linking stuff, because I assume not everybody's familiar with how linkers actually work, go into why Rock's special, and how we can take advantage of that. So this is the theoretical goal right here. We want to feel like a dynamic language while being a static language. We want to be as fast as Python when it in this case, it's a simple argparse program. I give it an incorrect argument and it prints out the help message. I want to have that experience where it's essentially instant and nice, but in a compiled language. And so in Rock, we start, this is using our basic CLI app, which is a little bloated and has some minor issues, but we'll talk about those some more later. But the front end, fundamentally is close-ish. And it's actually doing a ton of extra work it shouldn't be doing, and I think it should be at least half that size, if not even smaller. And so we'll move on, that's okay. Then we had LLVM, and we're like, oh, yeah, you can already feel it. That's enough that it doesn't feel instant. It's not terrible, but it hurts. So, okay, then you go to the dev backend, and that's not an error. It takes 1.5 milliseconds. It's apparently really fast when you just dump bytes to disk directly from your AST. It's not optimized, and, we have some work to do there to make it a little bit more balanced, but it's fast. And then they go. execution, we're all good. That's close enough. And obviously, given this is a talk about linking, there's a missing piece. Yeah. Well, that was nice. I'm glad that we really all just get to sit there and wait for the linker to think what it should do. Yeah, so let's look at that a bit more. LD takes about 400 milliseconds to link this. This is on a Linux machine, 12-core, standard Intel processor, nothing too special. And so you're like, okay, but I've heard of faster linkers. There's this old one. It's called Gold. Look, it's a bit faster. There's this newer one. It's called LLD. Look, it's almost twice as fast. Again, you're still clearly feeling this. It's not great. And this next number actually surprised me, because when I first worked on a surgical linker, this number was almost tied with LLD, but now Mold is about half of LLD for linking this application. And that really impresses me. One of the big problems I have with Mold is it only works fast on big applications. The smaller you get, the closer it is to LLD, which is fair, but it just means that your iteration loop may not be that nice a lot of the times. And even this at that's about as long as the LLVM debug build backend was, and so it's not like a nice experience per se, especially, it's feelable still. And so if you put Mold into this graph, that overall is something you can feel. And the other thing that really bothers me about it is we control the Rock front end, the dev back end, kind of the execution speed, but that's more how someone develops to some extent. But Mold we don't control. And so we're just stuck with this block here. And so the question is how fast could we be? Mold's here. It's what is linking doing? It's just basically copying files. So what if I was just to copy a file that size, cold cache? That's 15, 20 milliseconds to copy the file. This is a few megabytes on my machine. And you're okay, what about with a hot cache? Okay, so now we're looking at that, and it's 5 milliseconds-ish, though it's hard to say exactly because it jumps around a lot. Okay, and so here's the surgical linker. It's faster than just copying the file if it's a cold cache. And, this is not quite an order of magnitude over Mold anymore because it got faster, but it still is pretty darn close to an order of magnitude faster than Mold, right? And so there's this huge gain we can make, and so I want to talk about that. So first, I have to give some background context about linking itself. Why the heck is it slow? What is it doing? And for that, we have to talk about elves, the executable and linkable format. This is what Linux uses. There's Mako for Mac. I don't want to touch that. But for Linux, it's well documented and pretty nice. And so we'll just talk about that one, which is what the main running surgical linker does. But we also have something for Windows 2 and different pieces in progress. But it's a pretty simple file. It's hi, I'm an elf. Then it's here's how the program works. Then there's a bunch of data that's your actual program and the stored data. And then there's some other headers that kind of give metadata. Okay? So the elf headers give you a lot of things, right? But it's just the high level organization. It's oh, hey, we have 10 sections. They're over here. And oh, hey, we're using Little Indian, not Big Indian. And it's a 32-bit ARM processor. All of those different pieces. It's nothing too interesting, really. Then you get to the program headers. These are the really important piece for actually executing something. They are required in all executables and shared libraries, and it's basically hey, here's how operating system you're going to load me into memory. I want this over there. I want this space to be filled with zeros. I want this space to be unique per thread, which is what TLS is the thread local storage. These are all readable. I really would not like you to let someone write into my code segment, please. This is what this is requesting. And then there's this one special segment called dynamic. And one of the really weird lies about linking is that it stops when you make an executable. There's actually a second linker that runs when you load your executable, normally called a loader, but it is literally doing the exact same thing as linking. So just an interesting note that linking doesn't even end when the executable is created. And then you have the section headers, which is what the linker cares about. This is not needing an executable, but it tells you all of the really important pieces of information related to each different piece, what constructors do I need to run when the application starts up? That's what the init array is. All of those have to be merged together so that they can all be run at the beginning before the program launches. The finish array is your destructors. There's also a pre-init, just in case you need constructors before your constructors, important things. And then you have some more minor things, like here's all of the symbols, which could be variables, could be functions, etc. And related to that, here's all this table of strings because they're dynamically sized, so we need them in a separate table so we can tell where things are. And then there's reallocations, which we'll get into right here. So this is just the symbols and reallocations from a Rock platform, application. And so what we can see here is the first two things here are essentially the standard library, just a couple of standard library functions, which are embedded in the application. Then we can see that there is an effect that we're going to be calling that lets you print to standard out, theoretically, right aligned to it. Then you can see these rock-alloc and rock-realloc, which are special rock things. And in this case, we're saying they're undefined. So this is where the linker really comes in. Of like, at some point, someone needs to like define that, right? Like, I can't just run code with undefined functions. And so the other important thing is relocations, not allocations, sorry. Relocations, which is basically your list of edits you need to do to finalize the application. You know, they're going to say, hey, in the text section right here, I need to call memcopy. I have no idea what that is, so please, put the address of mincopy in for me. Or, hey, I need to call rock-realloc. Put the address of rock-realloc in. Or, hey, I need to point to this data that's in another section. I know it should exist, but I need you to, update the pointer. And some of these even get more complicated, but, for our use case, it's mostly just these direct and simple relocations that we're fundamentally running into. And so this is where scale becomes important. So this is hello world in C. Hopefully most of you can read that, not too hard. What does it end up linking to? You put the verbose flag in and you see a lot of stuff come out that gets passed to this linker. And most of this stuff is this CRT, which I should have double checked, but I'm pretty sure it's common runtime. But anyways, it's important stuff for actually beginning and ending the program, what actually happens before main, all of that fun stuff. We have our actual object file. Then we have libgcc, which to my understanding is kind of extra filler primitives that you may or may not need when you compile. And yes, even Clang uses it. And then you have your standard libc, which almost always, though not in the case of Muscle, ends up being a dynamically linked library. And so this is hello world, right? This is going to be a tiny executable. So what are we processing here? So this is 7 megabytes of data for hello world that's getting processed to build hello world, which depending on who you are, you may say that's ridiculous, or you may be 7 megabytes, everything's bigger than that. But at the same time, we have to go and read all of those 7 megabytes. We need to then notice that there are 4,000 different symbols and 9,000 relocations for us to process and complete. And so we're going to take all of these pieces. We're going to do a little tree shaking to delete a bunch of stuff that we realize is not needed for the final executable. We're going to jam it all together. And then we're going to go through, and for all of those 9,000 locations, we're going to go and say, oh, this one needs to point to here because that's where I put in the final executable. This one goes there. Oh, and this one, we actually don't truly know the final address, so I need to make a dynamic, relocation to be run at runtime to get the final relocation. And so even this basic Hello World app is consuming a lot of data that needs to be read through and processed and takes a solid amount of time. There's no way around it. You're reading 7 gigs of data, or 7 megabytes of data, God, not 7 gigs. We're not building Chrome. But we have to read all of that, and we have to process all these relocations, and we can try to do it fast, and we can try to do it in parallel, but for the most part, this is a relatively linear operation, and that's why LLD is so slow at it, and Mold has figured out how to parallelize some of it, and so it's faster, but this is the complication we're dealing with. And, I mentioned that basic CLI is a little bloated. So this is, it has all of the things you might need, right? Rock is built on platforms, and platforms have to define everything you're allowed to do. So for basic CLI, you might want to access file IO, you might want to do some directory stuff, you might want to look at environment variables, SD out, etc. And then on top of that, we have some HTTP stuff, and that's actually where most of the bloat comes from, depending on certain Rust libraries. Rust is also just maybe not the most bloat-friendly language. It likes big executables. But anyways, what Rust generates as the piece we link to is about 45 megabytes. And in that, instead of just 9,000 relocations, we're at 400,000 relocations. And so this is why it takes 80 milliseconds for even Mold with its parallel processing and all of its fancy tricks to link this thing, right? it is ginormous. And we have some ideas of cutting that down to save time, but fundamentally, anybody who makes a reasonable sized application is going to hit this problem, right? It's not like this is some giant crazy application. We're not talking about Chrome where it compiles into multiple gigabytes. We're talking about something that the final compiled artifact is just a few megabytes, right? And so like this clearly adds up. And this is not including other shared dependencies that depend on libc being the most obvious one that it's definitely calling into. And so now the important question is, why is Rock special? Like, why do we get to cheat and other people don't? So Rock is built on a stack, like Richard mentioned, of application, then platform, then operating system. And like, yes, you could say, well, like, you know, there's the host language and blah, blah, blah. I just throw that in the platform. I don't care how it does things. It's this stack. And what's really important is the separation between Rock as the application and the platform. So Rock is all 100% pure code. It does nothing. Okay? You can't do anything with Rock alone. I mean, okay, if you're in the REPL, which can cheat and print things, you know, you can like see an algorithm run. But fundamentally, Rock by itself just makes heat. And we have, you know, the asterisk is there. Okay, we force the user to allow us to panic and allocate memory of the platform. Okay, so we have two side effects, allocating and panicking. But otherwise, we just make heat, okay? And then we return something back to the platform and like say, hey, platform, I'd really like you to do this thing for me, you know? That'd be great. And this leads to something really important. If you look at a Rock application, and you look at all of the different the different functions that it cares about, they're like all Rock underscore functions. They're like, hey, these are all the things that are just always required, the Rock alloc, Rock dealloc, etc. I guess I'm supposed to be waving that way, but I'll get there one day. And then you have the effects, which is platform specific of like, what does it actually allow the application to do? You know, maybe it can read a file, maybe not. That's totally up to the platform. And then there is another special category. So like memcopy and memset, LLVM just makes those when we do optimizations. It's like, hi, you had a copying loop. Here's a memcopy. Don't do that. And so like those appear. And then there's some compiler RT things that appear when we do more complex math, right? And so those are clearly important. In our case, what we do is we go to Zig and say, hey, Zig, can you bundle these things? And oh, hey, Zig, here's an implementation in assembly for memcopy. Please just like throw that in there. And so these we actually don't go to libc or to compiler RT to get in like a linking fashion. They're just in the Rock application already, which ones we need. And so you start thinking about this. It's like, you know, this is kind of like a really slim set of things we depend on. It's like just the platform. So like, what if we like could do something where we just like link the platform and then later we just add the Rock application? Because the Rock application just depends on the platform. Nothing else, right? So like that can't be that hard, right? This sounds feasible, right? And look at all these benefits. 400,000 relocations for basic CLI, gone. Good riddance. You know, there's our time savings right there. We're not doing that. We also don't have to scan a bunch of libraries, megabytes of data. We don't have to shuffle anything around. You know, because the platform's pre-known, we can like pre-compute a bunch of crap. You know, this sounds great. Like, why doesn't everybody just do this, you know? Like, as long as we can define a nice API, like, between these two things, suddenly there's all of these problems that we can just have done. And anything that's already done doesn't take more time. Crazy thought. And so, quick aside, you may have heard of this thing called dynamic linking. It's meant to do exactly what I just talked about, kind of. In that you're going to get a bunch of shared libraries and an application, or like that has to load them all, and it does the linking at load time. But like fundamentally, you can define this simple API between two things, and like you can make actually Rock generate a shared library, and in that case, you don't have to process the entire platform, and it does save a lot of time, though for other reasons, things like LD and whatnot still are really slow at making shared libraries with no dependencies. I think they like to scan things anyways, just in case you need them. But besides that, you know, you could do that, but we really want this nice, like, distributable executable that I can just hand off. So dynamic linking is not a solution here. It simply does not solve all of the problems. But, you know, a valid thought, especially if you're in other languages and you'd like some faster linking, dynamic linking can help. by reducing the problem a little bit and allowing more of it to be pre-computed. So now let's actually go to like what we do with the surgical linker. So the surgical linker is split into two different phases. We have pre-processing and surgery. Pre-processing is pretty simple. You compile the app as if it's a dynamic library, because that's basically what we want, or as if it wants to dynamically link to Rock, because that's basically what we want anyway. Like, it feels almost like the same picture, and sadly, compilers today don't like to generate what I want, so screw it, we'll just pretend we're dynamically linking, build the platform. All that pre-processing, complete. All of that, like, all those relocations complete already. And so then we get into the real pre-processing step. And so what we're going to do is we're going to scan everything ahead of time. We're going to save all of the information we need about like the functions we might link to, where they are. We're going to save, what things still need to be resolved in the platform so it can call Rock. And we're going to go and we're going to say, hey, we're going to delete anything related to dynamic linking right now so that you don't actually think you're a dynamically linked application. Then surgery, pretty simple. You put the app at the end of the rest of the code, and then you just fix everything. How hard could it be? So, yeah, here's really what happens with pre-processing. We literally compile as if you're going to dynamic link. We then have to shift the entire application's body. That's something you have to be careful on. It's an easy way to get lots of seg faults if you don't know what you're doing. Apparently, application code doesn't like to be moved. But you can do it if you're careful. And so now we have space to add a few more of those program headers we talked about before. Because Rock will need them, right? We have to load the Rock code somewhere, right? And then, as I said, right, we're going to collect all the dynamic information. Where are its function symbols? What are the relocations that it still needs to have done? We're going to collect that information, just save it to some metadata. And then we're going to delete the fact that it thought it was dynamically linking to Rock at all. We'll just remove that so it doesn't need to think it thinks it's static now. Cool. Then, we compile our app to machine code, use the dev backend, make it fast. We literally append the bytes on to the end of the binary, load everything up in a mmap, so we can have, things pretty fast. And because we just created a lot of these bytes anyways, everything's hot in cache. And now we just write some new program headers. We need one that says load all of our code. We need another one that says load all of our data. We sometimes need a third one that says load all of our mutable data for certain things, but Rock doesn't really have that issue being pure. And then from there, we literally just have to go through and fix up all of these pieces. We go and say, here are all the relocations that are in the application. And this is a super narrow set of relocations because it's just those, that boundary line. There's never going to be a crap ton of those. The boundary is a slim boundary for a reason, right? Even in an application that does a lot, you might have hundreds or thousands, but not hundreds of thousands. And so this is a tiny little problem. And because we already have so much of this pre-read, it's not like we're scanning any extra files. It's not like we're doing anything extra that we don't need. We load our metadata, and then we just say, oh, here's one, update, update, update. Just go down the list, And sure, we're jumping around memory a little bit because we're just going down the file and relocating whatever is needed. But it's super minor. Then we update the section headers. That's optional. It makes it so that it's a little nicer in the debugger, but section headers are only for linking and are not for actually running the code, so they don't technically matter. And from that point, we're done. We just kind of skipped most of the linking and just did this slim little surgery to do what we needed. And so this is one of the really important notes. This is 2,000 lines of code. So what I described there was all of the core concepts you need to do this. It's not like it's some complicated thing to figure out. Now, we do have a library that knows how to parse object files that we depend on, but I could write all those offsets and all those constants. That's mostly what we use it for. It's not hard. Just go read the Wikipedia page, some of the ELF documentation. It really wouldn't be that many more lines of code if we were to embed that in if we really wanted to. And we do have a few pieces missing. There's a certain category of relocations we don't support yet that will make things a little spicier. Because they relate to absolute things that then need to be dynamically corrected at runtime, and they're just a bit more of a hassle. Currently, the Rock compiler just doesn't generate those. It's nice to us, but we can fix that. There are plans for it. It just hasn't been done. And then we don't yet support debug info because Dwarf is a whole nother beast, and I'm just not ready for Dwarfs. Dealt with elves one step at a time. And for reference, if you look at LLD, it's like 120,000 lines of code. And if you look at mold, it's like 600,000 lines of code. Now, I've done no digging into any of these to like actually see how it's allocated, if they're vendoring libraries, etc. I just ran a line of code tool on their repos. And so like this is what we're looking at in difference, right? And again, the Rock front end should get significantly faster. Right now it's doing a bunch of extra work that shouldn't be needed, to my understanding. But that's besides the point. But we're going from this world where like it's not at all pleasant, because every time you hit go, you sit and you wait, and then it pops up. And like it just sucks. It's like a terrible feeling. Versus on the other side, you can hit go and then it's just done. And I get it. It's still not quite as fast as Python. Maybe with front-end optimizations, we'd feel like a dynamic language. But I think this is something more languages need to search for. Is like users clearly like dynamic languages for their development loop. This is like very obvious. So like how can we make languages that give you the same development loop while giving you all of the nice type checking, all of the nice benefits, etc.? And you know, Rock's tracing that. Rock really wants to be able to compete with a Python and feel just as fluid. Zig obviously has some different goals, but clearly in its simplicity and fast compilation is like important. And so like this is something that I think more users need to think about, is like, how do we build software that users love? And like this is a clear part of it, you know, a part of the picture that sadly gets forgotten at all the big companies, where they have infinite servers and remote builds, and where they just have, you know, all the time in the world for things to build, and very complex caching systems and things of that nature. But like that's not the average user. That's not the average experience. And this is clearly important for building something nicer. So fundamentally, cheat more. By that, I mean details matter. That's really what this talk is about, right? Like the solution is actually really simple, but it took a long time from going from like, wait, could we technically do this? To like, I'm pretty sure. I mean, Elf says this is how it works. And then just hacking something up and trying to play with it. And, you know, it's not perfect. As I've said, there are missing pieces to the surgical linker, and the Mach-O version just is fundamentally broken right now and is going to be a pain to write. But like most of this was just me and some other folks on Rock going and saying, what are the details? You know, what do we actually care about? What matters here? And really learning our systems such that we can take advantage of them, right? It's not really cheating. What we did is realize we're in a constrained situation, so we should take advantage of that. I think, like as with Richard's talk, a big problem today is that we keep building up higher abstractions and getting lost from like what all is at the bottom, what's important, what's actually happening. And like if you don't know those details, you really are not likely to build something that's nice, that's lovable, that's amazing. And yeah, that's my talk.
Thank you very much. Come back to the chairs so we can do the Q&A. August, okay, armed with the microphone. So, question from the audience, of course. So,
oh no, I'm scared.
You know who that guy is, right? He's the macho man.
Yeah.
Hello. I have a few questions, but I can ask one for now. So, you're targeting a shared, like you're building a shared object, right? And then you emit dynamic relocations, then you delete them. And you make, so everything is built as pick or pie, correct? So
yes.
You skip TLS. Did you know that when you do that, you emit general dynamic model, which is not efficient at runtime? Is that only for debug or is it for release as well? Because so basically when you take that into account, the linker relaxes a lot. And I know this is like a lot of work, but it does that depending on what you link. How do you handle that? Or do you handle this?
So in our case, a lot of things don't exist because of Rock, and so we do skip a lot of things. But I would say fundamentally, like we end up going and patching up a lot of things and like making them into direct calls. Currently, we actually scan the assembly and like find calls and then update them. And we may or may not keep that. But like for us, the call cost isn't generally that big of a deal because these are our big IO tasks that are awaited in an async model. And so I don't think that ends up being a trade-off we have to consider nearly as much as like, you know, if you're writing something with normal CFFI that's getting called back and forth all the time, like that will be a very different model than what Rock ends up building with its like async state machine essentially that it's always building off of and running off of. But I would definitely have to think more about your question before I give a good answer, because details are hard to just like picture in my head and figure out.
Okay. So final question. I'm not going to like hog the time here. Dwarf. When you link, you get rid of all the relocations for dwarf. How are you going to handle this? Actually, parsing dwarf is really slow. Everything is lab encoded, and you haven't included that. So I wonder how much of time you're actually going to spend on doing this, and if it's going to be worth it.
Yeah, I know that dwarf is going to be a big pain. Also, certain dynamic relocations that we have to omit, like the section won't have enough space, and so we'll have to like shift the whole binary more at our final compilation time. And so I know these are going to be big pain points, but at the same time, like even if that doubles the time the surgical linker takes, which right now is really the time to write a file to disk, right? Like there isn't like actually a computation time to the surgical linker for the most part. It's really just the mem map flushing to disk. And so like, I'm not super worried about it, but I do agree that they are like these big pieces that will require much more complicated surgery. And so they will take significantly more time, but we're still cutting off, 400,000.
Yeah, it makes sense. So a bonus, this is not a question, like there is a light in the tunnel. If you write a parser for dwarf, you can reuse it for Mako because Mako doesn't have relocations. So if you want to write this immutable, you have to do yourself.
Interesting. Yeah.
I think you guys should have lunch together. I mean, everybody else in the room is thinking the same.
Yeah.
Does it fundamentally not allow, or I missed something, any kind of FFI with C?
So yeah, Rock makes the platform decide everything. So there is no arbitrary FFI. And that's very pertinent in the design of Rock, in that we want everything through this effect model. And so you can't do arbitrary FFI and load weird other modules through this effect thing that's controlled by the platform. It's not extensible in a way that lets that happen. And so the platform has to decide how FFI works. And that could mean that the platform even allows calling into libFFI and loading things dynamically to do that type of stuff. But it is a restriction on Rock in order to maintain its purity and avoid libraries that can do horrendous things.
So no DL open, TLDR.
Nope.
All right, thanks.
Any more questions? Raise your hands if so. I say one. Let's make it the last one.
So have you thought about how would you do this for SIG, for example, that has a fundamentally different model?
Yeah, so I do think this can be done for more programming languages, but it's really about needing to know where your API boundary is that you can kind of cut things off at, and then tailoring to that. So in our case, we have this super duper clear API boundary, but there's nothing stopping you in Zig to model such that this core business logic part of your application depends on only a certain set of things. And so you could always surgically link it in to make it fast, right? It's just as about that slim API and not allowing it to do just anything. And you could even still have it calling libc or other things of that nature, but you need to define those in such that you can avoid these extra costs of needing to load and scan libc and do all of those other pieces. And so I do think it is possible for this to be expanded to a lot more languages, but it is a much trickier, more project dependent thing for this tool.
Awesome. Thank you. So I would say if you have any more questions, find Brandon afterwards, talk to him. You will have to wait for Jacob to be done first, I think. But now we're going into the lunch break, so there's definitely going to be time. Brandon, please give it up for Brandon. Thank you.